Welcome to the Global Composite Expert Webinar Series. My name is Wenbin Yu, Director of Composite Design Manufacturing Hub. This webinar series is to examine the history, present capabilities, and the future of composites, with the goal of sharing the knowledge that has been developed over the past half century. This webinar series is initiated by the Composite Manufacturing and Simulation Center at Purdue University. We reside in this beautiful Indiana Manufacturing Institute. I hope to welcome all of you to visit us when we get over this pandemic and when our life returns to normal. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of the resources for composite design and manufacturing. CDM Hub provides a very powerful website, cdmhub.org, for the composite community to carry out this mission together. We imagine CDM Hub to become the premier resource for composite design and manufacturing. This webinar series is one of the initiatives CDM Hub started as a service to the global community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, Cytec Solving, MSC Software, and Modex 3D. We greatly appreciate their financial support for CDM Hub. We also invite more organizations to join them to support CDM Hub's mission of serving the global composite community. This webinar today will be recorded and made available on cdmhub.org, and an email will be sent to all of you once the recorded video is available online. The presentation will last around 40 minutes. We will have about 10 minutes to 15 minutes for questions and answers. All attendees are muted. Please submit your questions through the Q&A box. After the presentation, your questions will be read and answered. Next, I will ask Dr. Byron Pipes to introduce our speaker today.
Welcome, everyone. We're delighted to have you here today for our expert lecture by Professor Kevin Potter. Kevin Potter is the Emeritus Professor at the University of Bristol in the United Kingdom, where he worked in Advanced Composites Center for Innovation. He earned a BSc degree in Materials Science from the Imperial College of Science and Technology in 1974 and has spent almost all of his career since then working in the design, manufacture, and assessment of composite products, mostly in an industrial setting. Since joining the University of Bristol, he has been responsible for developing and running a number of research programs in the general area of materials and manufacturing. These include looking at the innovative approaches to composite structures, generating an understanding of dimensional variability of composite components, developing technology to control crack propagation in bonded joints, and improving the understanding of reinforcement deformation and drape over tool geometries. Almost all of the work is carried out in collaboration with industrial companies such as Airbus, Augusta, Westland, and Bombardier. He is also interested in the design process and in the training of practicing engineers in the use of new materials. Indeed, he acts as an enterprise leader for aerospace engineering with the aim of encouraging enterprise among both students and staff. I give you Professor Kevin Potter.
Okay, so my talk for today is the title here. So what I want to talk about is how we've got to where we've got to, in effect, in terms of automating the layout of complex composite structures made up from pre-impregnated reinforcements. This presentation largely emerged from a series of conversations that I had around this time last year with friends and colleagues in a visit to Zhejiang University. And since I've retired, in inverted commas, from a university recently, after 25 years working in academia and more than 45 years working in composites, I started to give some thought to these few questions that I've listed here. Firstly, how do we choose the topics that we choose to expend our research resources on? We have limited resources. It's quite an important question, not necessarily a question that is often asked. But we might think in that in terms of, say, do we look at nanocomposites versus cost-effective composites? Why have we not made more progress in automating the complex parts of the composites world? Simple components we can make automatically, more complex components we can't. And we might think of that in terms of, do we need better robots? Do we need better ways of supporting humans? And lastly, and potentially in many ways the most important question, what's the best way to teach composites at undergraduate level? And what's the best way to train practicing scientists, practicing engineers in composites at master's level and at doctoral level? And we might think of that as the tension between deep dive science or broad horizons engineering approaches. Well, I've given it some thought, and it turns out that when you start to put some thought into this, that really all three of these issues are aspects of a single problem. I don't think there's really a name for it in a sort of philosophical or other sense. It's really trying to understand the messy bits of reality, the bits of reality that don't necessarily conform terribly well to our conventional linear scientific approaches. But I've only got a limited time today, so I have to choose one of the three. And what I'm going to be talking about, obviously, is automating manufacture. So the subject today, I think, is best expressed as a question. Why, after 45 years of trying, have we made so little progress in automating the layout of prepregs into components of complex geometry? 45 years is almost exactly the length of my career to date, so it's perhaps my problem that we haven't managed to get to where we'd like to be. I think it's worth saying a couple of words, though, about a definition, how we define complex geometry, because that really underpins everything else that we're doing. So when I say complex geometry, I would like to distinguish between complicated geometry, say a string of stiffened panel built up from a lot of simple parts, and complex geometry, which might be a panel with multiple changes of double curvature, lots of features that intersect with one another, or changes in features locally. And it's something of an open question, I think, whether complex geometry, in that definition, also leads to complexity in the sense of coupled nonlinear behaviors that approach the chaotic. We might start to get towards that question by the end of this presentation, but only might. So these are examples of complex geometry. The one on the left is the inner door panel from a supercar. It's about as geometrically complicated as any ever going to get. Each individual ply has built up from lots of separate pieces, very carefully laid up, very expensive, very time consuming. It won't come as any great surprise that the ticket price for that car was in excess of $1 million when it was made 20 odd years ago. On the right, we have a test geometry. We've used this regularly in studies of drape simulation. It deliberately was chosen as being as far from a hemisphere as it's possible to get. It probably represents the most complex geometry that you could realistically try to form from a single sheet of a woven reinforcement. So I'm limiting this presentation to prepreg. I really need to explain why I'm doing that. And mainly because although some of the problems with prepreg layout can be tackled using variants of resin transfer molding. I don't want to get sidetracked. I've only got a limited amount of time, so I'm going to largely restrict these comments to prepreg. I'm just going to say for the next couple of slides, talk about some of the issues with resin transfer molding. And we have a picture here of what's called the side frame of a BMW i3 Lifestyle. It would be a struggle to manufacture in prepreg. It's assembled from a series of preforms, each of which is pressed in an automatically fed and automatically handled press tools. So it probably represents the state of the art in a commercial environment in the 2013, which is when it was put together. I would like to contrast it, though, with a part that my team built 25 years ago, which is shown on the top left. Now, the i3 has 9 preforms, largely relatively simple geometry, pressed, and that they are assembled then to make up the side frame of the moulding. I have here the part that we made all those years ago. As you can see, it's a long way from being geometrically simple. We needed to actually make 33 preforms to build that component. They're made of carbon tape and woven cloth. They build up a complex 3-dimensional assembly that tracks the loads through the entire structure. They too were made by press form and preforming, some in single part tools, some in double acting tools. And the big difference is that we had to make everything separately, whereas the BMW parts are relatively simple and straightforward. In both cases, getting those preforms actually into the tool was done manually. Still is done manually in the case of the i3. So it's not an unreasonable question to ask then, just how much progress have we actually made in 25 years in being able to handle some of these complex geometries. I have another example here, which is a part that actually I made myself, my own fair hands, when I was about 24 or 25. What we've got here is a section through a prototype helicopter tail rotor gearbox casing. And I say it was made about 40 plus years ago. It used a very novel aligned short fiber prepreg and another specially developed 3D format short fiber autoclavable molding paste, which we needed to be able to mold the 6th flange. It was, I think, probably about a reasonable idea of the state of the art at the time, probably ahead of its time. It was in a paper in ICCN 2, for those whose memory go back a very long way, but really a footnote today. The only 2 reasons that I mention it are, one is that there's a lot of work again today on short aligned fiber molding compounds and short aligned fiber molding sheets. And the notion is that they are going to, because they are formable in a similar way to metals, that they can simplify manufacture. And although it's true that they can, the part that I've just shown can't be stamped out, and the majority of parts can't be stamped out. And if you think about the analogy with automotive steel pressing, the system there is not automated steel pressing. It's automated steel pressing and spot welding. And the spot welding bit is very important. So what I am sort of suggesting here, not saying that we haven't made progress, but I am saying that the progress that have made has been ad hoc. Everybody's answered their own questions rather than being developed or generalized into a wider theory of composites manufacture. From an industrial point of view, I absolutely understand why you would do that. You don't want anybody sharing your IP, copying your ideas and so on. From an academic point of view, I think it's a missed opportunity not to have tried to build something wider. Just as an example of where things can go wrong with this sort of ad hoc developments. My last job in a factory environment was troubleshooting a line making complex geometry honeycomb cord sandwich panels for aircraft wings. We had significant problems on that line. We had production rate which was way behind targets. The right first time build quality was very poor. Many parts had multiple concessions within each part. Every manager that was on the line had a different opinion, and the only agreement was that something had to be done and had to be done now, but nothing worked. Then we started doing some proper data capture. Once we had good data, we started to know which of the panel sets gave us the problems, which design features and production practices caused our problems, where the problems were, and therefore what we might start to do to fix them and get back on track. But we got to that point. I collected what we thought were our major problem areas, went into the scientific literature, and there really wasn't anything there. And the scientific literature on composite manufacture at that time that could really have helped us significantly. I'm sure the position's better today, but I think we're still a way off perfect. If anybody can point me to a composite production line that is operating Six Sigma quality in terms of its Tyson rejects, I'd be very, very happy to visit it, but I don't know of any such facilities. So we got to where we are by traditional approaches. Is there another way of trying to make progress? So what I've done is I've decided to try something completely different. Doing more of the same as I have been for the last 45 years didn't seem to be a very useful approach. So what I've tried to do is this, what I call a one-man brainstorm. My methodology simply was to sit down in a quiet room and write down all the words and phrases that popped into my head in relation to manufacturing composite parts as pre-preg, but what the problems are and what the solutions might be. So I wrote them all down in my head in exactly the order that they arrived and placed each word into one of 5 categories. And the categories are system level issues, problem areas, open questions, possible enablers, and possible solutions. I should say that sounds very clean and tidy. What I actually did was to group the words into sets that appeared to have common features, and then gave those common features the names that you have here. Most of the words were actually quite surprisingly, in some ways to me, fell quite cleanly into one classification or another. And that I could then make a sort of sorted list. So what I have here is an unsorted word cloud, exactly in the order that the words presented themselves and I wrote them down. I'm sure a good psychologist could decode probably from this list what I've spent most of my working life doing, what I've spent most of my working life beating my head against the wall about. But to take this and we start to look at it in a little bit more granularity. So what I've looked at is the system level issues firstly. So things like, how do we define productivity? What do we really mean when we say we want more producible designs? What our decision-making processes are. Do we really want to go for full automation? Or would it be better to use the undoubted capabilities of humans in terms of manipulating materials, but to improve their support and to eliminate some of the problems that we have with using people in this? Then questions like around how do we develop the right business case in order to fund the research programs that we might need? How do we define producibility? Do we need to completely reappraise the whole of composite manufacturing, or fix things one bit at a time? We can move on from that and look at the problem areas in our current approaches to automation. So one obvious problem area is actually getting the backing paper off if you want to go for a robotic solution. Then there are simple things like reliability, excessive downtime, limited geometries that we can handle, reproducibility in terms of process variability, reproducibility in terms of materials variability, very high machine costs for some of our automated designs and automated machinery and so on. But we're starting to collect ways of our problems. And then we can come into what I've called open questions. These are areas that we don't really have a good answer or don't necessarily know the problems to all extents and purposes. So things like how do complexity and part cost connect to each other? What sort of metrics do we need to have in place for productivity? What manipulate in a technical sense? How can we describe the manipulations that we need to get our prepreg onto the pod? What's our reinforcement mapping strategy? Can we develop a taxonomy of complexity to be able to actually understand and discuss some of these issues better? Do we need end-to-end workflow automation? So these are all very simple questions that we need to start getting better answers to. And lastly, we have the potential enablers. These are things that we might have pointers to a good technical solution. So things like design for manufacture knowledge bases, soft robotics, getting the right metrics and targets in place, things like using augmented reality approaches and haptics with robots and training approaches, virtual reality approaches to training, for example, and then there are things like standardizing the tool sets. Better training for laminators is always a good thing, and actually better training for designers is probably even more important than better training for laminators, because it's the designers that give the laminators their task. And lastly, what we have here are possible solutions or possible elements of the solution. So things like one-shot forming, using the right manipulators. I've got down there AFP crawlers. If you imagine trying to run an AFP approach to making a wind turbine blade, which is 100 meters long, you are going to have a hugely expensive gantry system. Or why not just have little trucks that run over the surface, laying prepreg as they go? You can have a flock of them and be very much faster and much cheaper than running a gantry system. So novel material forms. I said there's a lot of work at the moment in terms of more formable material forms, and it is absolutely a good way forward, but it's not without some issues of its own. And then we have things like the tack-on-demand prepreg, sequential forming, continuous toe shearing, which is an AFP approach where the material is manipulated in a different way, so that rather than having maybe 1 meter radius of curvature before we start to see significant defects, we might get down to 10 millimeters or 50 millimeters radius of curvature before we start to see defects. So there's a whole raft of possible solutions that we can come up with. Now, one thing that really jumped out at me was that the list of problem areas and the bulk of the list of potential enablers and potential solutions was in the form of very simple closed form statements, such as excessive downtime or high machine costs, or standardize your tool sets, or carry out workflow analysis, or one-shot forming, or cure on the fly. So closed form questions are basically the lifeblood of science and engineering. So if our problems, our questions are in that closed form, why have we made such limited progress? Because that's the area we ought to be able to understand and move forward in. On the other hand, if we look at the system level and the open questions, by contrast, they are very much in an open form. We actually need in-depth discussions to even frame the question properly, let alone generate a solution. So things like complexity versus cost levels. We really don't have any clarity about how to define geometrical complexity in a way that we can directly interrogate in a design or costing environment for either manual layout or AFP. I've said that at least not in the academic world. Now, there may be people in the industry who are looking at that and saying, well, of course we can do that. But the knowledge base doesn't currently exist in terms of papers in the academic world. And then again, we can look at the questions of complexity versus market size. We have have next to no idea about the relationship between the value of potential markets and how geometrically complex the parts needed to be to satisfy those markets. But I can't really build a business case to do more research without that level of understanding. And this slide, I'm trying to encapsulate here what I mean by this. So if we look at, we've got in the y-axis, we've got the market size, either by number of parts or by value, doesn't matter at this level of granularity. And then in the x-axis, we've got the geometrical complexity of the parts that we need to build. So the question we have to answer is, does a small increase in our ability to make more complex structures cost effectively have a big impact on the addressable market size, or do we need big changes? So if we look at the green line there, what it's basically saying is that if we can get our ability to handle complexity a bit improved, we can get a big significant increase in our market share. The red line saying the opposite, obviously, that we need a big change in our ability to handle complexity before we can see a big boost in our market size. And the reason that matters is shown here. On the green line, we can double the market size with a very small investment. If we're on the red line, it would take probably 10 times the level of investment to get the same level of return. As I said before, if we want to be able to understand how to build the next generation of composites and the next generation of composite market, it's very difficult to do that if we don't have a clear understanding of the relationship between market size and part complexity. So I've got to this point, and I need to sort of, in a sense, put my cards on the table. And my working hypothesis here is that a lack of attention paid to the system level and open question issues in the development of composite manufacture approaches has prevented the development of solid foundations on which to build a coherent approach to composites manufacturing science and practice. I'll leave you a moment for that to sink in. And the question then is, how do we take it forward? So what I've tried to do here is to redefine the problem a little bit in order to make progress. I've collected together all the open form issues. I've recast them into the form of a list of questions, and we can then try to use that list to identify what might be the critical development areas. I'm afraid the list is a bit long. I could try to synthesis or précis of it, but I think that might give the impression that we were actually more in control and had better understanding than we really have. So the next 3 slides, I'll go through what I think are the open questions. The first is, do we aim to develop full automation or systems to support humans in manual or semi-manual processes? Do we focus attention on the processes for particular classes of part or attempt a root and branch reappraisal of composite manufacture? How do we acquire the tools that we can use to support the business case developments that will be needed down the road? What's the most effective decision-making process that we can utilize? And how can we rigorously define and describe producibility? At the moment, people talk about producibility indices, but there's not a great deal of clarity about what they really mean. Another big area is the question of how do we most usefully describe productivity. Now, productivity is probably most often described in terms of kilograms or pounds of material laid down per hour. That's all very well, but it doesn't. It's only half the picture. If for example, I'm making something up which may be 2 meters long by 1 meter wide. I'm making it by using an AFP machine. The footprint of my AFP machine is probably 4 times the footprint of my tool. So if I'm building a productivity metric around kilograms per hour per square meter of floor area, my AFP machine is going to be significantly poorer than my manual lathe. If I'm building a productivity metric which is around pounds per hour laid down per $1 million of investment in machinery, again, I'm in the wrong place with the automated solution. We need to be really clear about the meanings of the words that we use and how we apply them. So that takes us on to how can we reliably link geometrical complexity to development and production cost and risk levels. There is obviously, and I'll show a little bit more about this later, but there is a big change in costs for relatively small increases in some aspects of complexity. What tools do we need to be developing for effective end-to-end, from conceptual design to end-of-life cost modeling? And again, it has to accommodate our geometrical complexity. What productivity metrics will give us the best understanding for developing our research and development targets? And how can we link geometrical complexity to the production volume requirements of different types of products? Moving on to the sort of last set of questions. How can we link geometrical complexity to the size and value of the different markets that we could address? I've seen over the last 10 years or so lots and lots of different market size assessments for composites. Most of them, I would say, are probably not worth the paper that they're printed on. There'll be some assumption of maybe, there's no composites in that market today. If there's 10% of that market taken by composites in 10 years' time, it will equal X billion pounds, X billion dollars, X billion renminbi yuan. It doesn't matter. What matters is understanding how to get into that market. And we can only understand that by understanding whether the processes that we have are appropriate for the geometries and the production volumes that we're looking at. Can we develop a useful and applicable taxonomy of geometrical complexity? The question really is, can we work out a way to talk about complexity in relation to composite parts that is directly useful in a design and manufacturing environment? Should we aim for a full robot solution or involve humans in the loop and get some sort of cobotics? Should we prioritizing rapid forming or geometrically complex forming? And then lastly, given that rapid layup is only one step in the total manufacturing workflow, is actually end-to-end workflow automation the real target, rather than what we tend to do at the moment is limit ourselves to layup. There are some other issues that fall within the sort of normal science and engineering remit that are really, they're very amenable to the current methods of academic research, but they're not really being studied to the extent that they could be. Two obvious ones come to mind. I'm sure other people could add others. So there's actually a limited amount of work on deformation mechanics of the prepreg itself. Uncured UD prepreg is generally not well characterized. It's quite variable, it's poorly understood, it's time dependent, and it's highly nonlinear in most, if not all, aspects of its behavior. There's also a very limited amount of work carried on the detailed manipulations and processes using manual layup of unidirectional prepreg or of woven prepreg. So we're often in a position of trying to automate a process that we haven't really studied in any great detail. So to take an example of this, drape modeling has been a major element of composites manufacturing R&D for a very long time now. We can try and trace its history. If I try and do that by putting drape into Google Scholar, I get a mess because drape has lots of different meanings, most of them medical. But we can search in Google Scholar for pin jointed net, which is the sort of general understanding of how woven cloths drape. And that will catch most of the Composites woven cloth drape papers at any rate. And what we see is that the first use of that term in 1979. Over the next 20 years, just coming around to the year 2000, there were 30 additional papers that use that search string. By 2010, we were running at about 100 papers. By 2020, when I checked this morning, there were 243 papers that have pin jointed net as a searchable term. Now, typically, those papers look at improving modelling or apply the pin jointed net approach to a specific geometry. In the broad sense, they're asking the question, can I drape this geometry with a woven cloth prepreg, rather than asking the question, if my reinforcement acts as a pin jointed net, what geometries or classes of geometry can I form? That is to say that we have lots and lots of papers that are asking the closed form questions. And I only know of one or two papers that are asking the open form question of, okay, I've got a woven cloth, what's it good for? We need to be a little bit more open to asking these questions that have slightly more complex answers. And I said I'd talk a little bit more about the effects of geometry. This is some work that we did in Bristol a few years ago now, and what we were looking at was the impacts of the geometry on the speed of laminators. So we got 3 laminators from 3 different industries. We gave them a series of tasks, layup tasks to do. You can see at the bottom of the screen there, the tool that we had. We had a little insert block, and we could change the ramp angle on that insert block from 20 degrees to 70 degrees. And what we found when we were down at the 20-degree end, they could lay up, all the laminators gave similar sorts of round, and around 25 seconds, they could lay up that part. When we went up to the 70-degree end, we were looking at about 250 seconds to lay up that part. So that, the geometry, the detailed geometry of that region potentially changed the rate of the layup by a factor of 10. It also would have changed the likelihood of getting significant defects. One of the sad but true facts of life in composites is that complex geometry regions tend to have higher complexities of stresses and be more sensitive to the origins and the initiation of defects. So our defects tend to fall into our regions of most complex stresses, which is kind of unfortunate from a sort of design and manufacturing point of view. But if your cost modelling tools don't capture the fact that minor changes or apparently minor changes in the ramp angle can have very major changes in your layup cost, you're going to have significant problems in making any money. It's even true, and you mentioned that as part of that testing that we did, we also got laminators to use different prepregs. And we were seeing factors of 2 in the time for laying up the same geometry over the same part by the same people with 2 different prepregs that were nominally as near as makes no difference identical. Although we're all sat in weaves and so on. So moving on, we need to work out what we can learn from these open questions. So many of the questions actually relate to trying to develop an appropriate language to discuss the wider issues. So things like complexity versus cost, production volume, market size, we need to define our terms with clarity and precision. So topics such as producibility, productivity, and the associated metrics, and taxonomy and complexity look at the fundamental structure of the language that we need. Once we have the language, we can start to build the understanding and start to make rational decisions about the extent to which we could or should attempt to automate, and then start to build a rational business case for investment. So what I'm envisaging here is a sort of 4-step process. And step 1 would be language development. So focusing on clarity of description of geometrical complexity and the related issues of producibility and productivity, trying to develop well-defined and usable metrics that can be reliably utilized by non-specialists. It sounds straightforward. I suspect that it's actually quite a long way from being straightforward. So step 2 would be data gathering. As I've said before, the current estimates of composite market sizes are generally being based on a series of assumptions without a very clear evidence base about why behavior should change. The sorts of developed tools I've been talking about could be used for a more rigorous assessment of producibility and costs for different potential products in different potential markets. This will then give us a much better clarity on which markets are currently ready for significant penetration by composites, and a much better idea of what we might need to develop to penetrate those markets that are not currently ready. Step 3 takes us into the decision-making area. This is sort of the point at which major decisions on development directions can be made, based this time round on much more reliable estimates of what we need to develop to penetrate markets and what further development is needed. That leads on to the last of the sort of 4th step process, which is business case development. This is really our last step. This is back in the realm of large business investments. In recent years, this is been in the area of national politics. Now, I'm well aware of composites manufacturing R&D programs in the UK, from the UK government, from the US, certainly across Europe. I sit on the International Advisory Board for the Japanese equivalent. So everybody's doing this. Everybody's building building manufacturing research programs. None of it is being terribly heavily based on solid data about what the problems are and how to move past them. We need this information really to be able to build the sort of future R&D on good solid foundations. And that brings me on to a project plan. So the language development activity, we really would want to start from productivity descriptors, as I discussed about. Without understanding what we mean by productivity, we have real problems. We need to we need some good geometry descriptors. Between our geometry and productivity descriptors, we can start to get a more formal understanding of producibility, how we might sort out what the metrics are for that producibility, and then start a metrics validation and dissemination exercise. That is that's the sort of classic project plan approach. Problem is, I have no idea how long any of that would take to do. I've got a series of numbers, units across the top. It would be great if I could understand productivity descriptors in a couple of weeks. I don't think that's going to happen. It would be great if it could be a couple of months. I doubt that's going to happen. We could be looking easily in excess of a year, even to get to the sort of the first part of this activity. So I think the big challenge here for me is that it's not at all obvious what skill sets are going to be needed to approach this sort of work. Lots of composite specialists, obviously, but we need people that understand geometry, knowledge, robotics, ergonomics, marketing, business development, and so on. I'm sure there's lots more I haven't even identified, and it would be critical, in my view, to have input from both academic and industrial traditions. There is no project plan steps 2 to 4. There can be no project plan beyond step 1, as that provides the basis for everything that follows. I could write one, but it would be essentially a fairy tale at this point. So to go back to my starting point, Is it complex geometry or complexity in the mathematical sense? Certainly, it's true that some aspects of complex manufacture involving interactions of materials variability and process variability on materials that have time-dependent nonlinear processes do seem to approach the chaotic, specifically thinking of some defect generation mechanisms. But I'm not actually convinced that they slip over into complexity. I am convinced that we need to understand much more than we do about how we can manage the design and manufacture system ecology and take a much more complete and system level view than we have historically. So I've laid out what I think is the best route to making step change improvements in composites, which is probably the opposite of how most scientific research funding gets done, where narrow depth is generally more prized than breadth of subject. I would honestly be surprised if I could get this funded, largely because I can't say how long it will take or that it will be successful. So before I close up, I just want to say, while I've got you here, I want to say a few last thoughts on research funding. If I put carbon nanotubes into Google Scholar, I get more than 1,000 papers, each which have more than 100 citations. On the normal metric of 1 in 20 papers reach that standard, we're looking at about a total number of academic papers in the region of 20,000 papers. And even at a very modest £10,000 per paper cost, that represents a significant slab of research funding. If I put production costing into Google Scholar, I get 6 papers that have more than 100 citations. Now, that's production costing. That's not composite production costing. That's production costing for all production. Composite production costing gets a hit. So the question is, do we have our priorities straight? Also, we should never forget that most of our scientific papers are generated by doctoral students. So there's an often overlooked feedback loop where, because our research funding decisions are actually also our training decisions. So if we decide that our focus should be on narrow specialisms, then that's what we send out of our doctoral training programs, and someone else has the job of socializing them outside of academia. The sorts of open-ended research investigations I've been discussing here would make very solid, very multifaceted doctoral studies and turn out very useful members of the community. So to close up, this is a long way from being original thought, but it is very true in composites manufacturing. Everything is connected to everything else. Holding it all in our heads is hard, but well worth trying. The only thing that will give us really significant progress is a holistic systems approach to making things work. Thank you for your attention. This is me sort of going into an unknown territory, so I'm certain that I will have made some errors along the way, and I would like to apologize now for my errors. Thank you.
Thank you, Professor Potter. My name is Jonathan Goodsell. I will be handling the question and answers here. As a reminder, please enter questions into the Q&A box, and I will field those and address those to Professor Potter. I think we all appreciate the open-ended questions that you've raised, and I would begin the question and answer by one open-ended question, and that is, what do you see as a forum for discussion and brainstorming and potentially even tackling of these kinds of open-ended questions that you've raised?
That is absolutely an excellent question, and it's one thing I've given zero thought to. It's a sort of thing that we might something like the problem is we need a forum where the industrialists and the academics come together. So SAMPI probably is the closest to doing that, but we probably need something within the sort of perhaps special sessions in ICCM or something like that, which are focused on discussions, because when we all go to conferences, we focus on putting our research forward rather than necessarily putting our research into comparison and seeing how our research fits with other people's research to build a structure in the right direction. I think the new centre at Purdue is probably very well placed to structure this sort of thing. And I think that's probably what it's going to take. It's going to be one of the sort of major players in composites manufacturing research to say this is something that we need to do. This is something that we need to focus ourselves on.
Thank you. Some very, very thought-provoking questions that you've raised here. Someone has raised the question that certainly as you have discussed in the aerospace industry, things are moving more toward series production. And in your opinion, how long do you think it will take for us to get to an end-to-end automation, as you raised that point today about not just the layout process, but the whole process? What do you see as a path forward there?
I think the first question I would ask is really whether it's entirely necessary. Because if you look at the automotive industry, for example, you talk to car makers, they're very clear that they don't care almost what the hardware costs, because it's amortized over very large numbers. In the aerospace environment, we're not, apart from the sort of 737 and the A320 series, nothing else is really made in big enough volumes. That it's not necessarily the case that the best solution is to try to do end-to-end automation. I think what we do need to do better is to understand the business case around why we would automate a particular area. So, mold cleaning, for example, is something that probably we could automate. But then you've got to put an inspection process in, and things can run away with you when you use people to do a job. You're effectively buying hands and a data capture system and a data recording system all in one person, because they are actually going to look at their own work and do a sort of quality control on it. If you use automation, so one of the big topics recently, for example, has been in AFP, is how to attach a camera to your AFP machine so that you are effectively recording everything that's going down. Whether that's a sensible thing to do, I don't really know. But it's one of those things that I'm a little bit concerned about, is that when people develop the ability to do things, like developing the ability to check every fibre that's gone down for whether it's straight and in the right place, your initial thing is that you find lots and lots and lots of defects. I'm a little concerned that we can be over ambitious about trying to find all the defects, because we can't actually get rid of them.
Mm-hmm. Another open set of questions then becomes, of course, which of these actually matter?
Yes.
We get more knowledge, but do we really have more wisdom there? Do we know what to do with it?
Yeah, I think that the move from data to knowledge to wisdom is it's a tricky path, but it is essentially where we ought to be heading. I mean, I can give you a sort of an example of that. I was talking about a line that I used to work on, making wing panels. We had not a huge, but a significant number of defective panels that were picked up by NDT. So that was fine. We could live with that. It wasn't too bad. So then we went to our customer and said, "Can we stop doing 100% NDT?" And they said, "No, of course you can't, because your panels, you're snagging defects." So I went back into all our NDT records at that point and found that there had not been a single case of a panel that had been trapped by NDT that should not have already been rejected because of either dimensional defect or autoclave. What was happening? The autoclave was causing us a problem, and that was causing delaminations, and the delaminations were being picked up by NDT. But people were, because of the habit was to keep panels in production and only basically sanction them at NDT, it looked like the NDT was doing a great job. In fact, NDT was not doing any job at all because we should not have been doing it. We should have been scrapping things earlier. But if you capture all this data and then don't change your behavior as a result of the data you capture, you can get yourself into this sort of situation where you're doing yourself harm by having more data rather than doing yourself good.
Very good. Thank you for that example. Let me return in the last couple of minutes here to a question again about these open-ended questions. And it's phrased in this way. Young academics need to consider their career in terms of publications and citations. The issues you've identified are not amenable to quick publication and high citations. So how do we get the best and brightest students to work on these issues?
I think there's two or three answers I would like to put to that. And the first is, what do you think your students are for? If you think that you are training PhD students solely to become faculty members of tomorrow, then you're doing the wrong job, because most don't. The vast majority of PhD students, at least the students we put out in the UK, it may be different in the States, end up working in industry or certainly outside of academia. Quite a lot of them are snapped up by the financial institutions because numerate problem solvers are always going to be in demand. So if you insist on treating your grad students as faculty of tomorrow, they will not be developing the skills that they need to do the best possible job for in an industrial setting where they need other skills apart from narrow analytics. So I think that's the first part of it. The second part of it is that actually some of my best cited papers over the years have been very industrially focused and have actually been directly looking at industrial types of problems. So I think that's probably part of it. And then probably the third element is that with the expansion of things like Google Scholar, it's now possible to find relevant research in journals other than Composite Part A or Composite Science and Technology. And that means that actually we can start to be a bit broader about in the journals that we publish in, and we'll still get the citations because good papers still get found basically. So I think a combination of those issues are probably where we need to be. And certainly within the Industrial Doctorate Centre that we've been running very successfully in Bristol for the last few years, all of our students are both doing industrially relevant work embedded in companies and publishing in good journals. It's just a question of knowing that you have to do both and setting your programs up in order to be able to meet both aims.
Thank you very much, Professor Potter. Thank you for your presentation today. We thank all of the attendees today and all those who asked questions. We look forward to joining with you again here in a few weeks. Professor Michael Wisdom will be speaking on November 19th. Thank you again for your participation, and thank you to our sponsors.